to our presentation. Now, before we get into the topic of today, I would just like to lay the foundation for those who are not familiar with calculus or do not know what calculus is. And to do that, of course, we need to know what exactly it is and why it is so important. Now, just for a bit of background, calculus was invented or developed by two mathematicians, namely Isaac Newton and Gottfried Leibniz, in the late 17th century. And although it can be defined in many ways, simply put, it is the study of the rates of change over tiny intervals of time. Now, calculus can be used to help us construct relatively simple quantitative models and reduce the consequences from it. This is what makes it so important, because as much as it can be used by mathematicians in mathematics, obviously, to calculate the slope of the curve and whatnot, it can also be used in various different aspects of our everyday life that you don't even normally think it can be applicable in. For example, astronomy, it's used by astronomers to calculate or to chart the orbit of the planets and the stars. In chemistry, to understand the path of electrons and protons in an atomic level. And in even medicine, to understand how the medication interacts with the body. These are only a few of the many examples of how it can be used. Now, with this understanding of what calculus is and its importance in our lives, we can now move on to the topic of today: differential equations.
Differential equation. Differentiation is a calculus technique that we use to analyze the behavior of a function in its rapid change with respect to time. This is where it's applied in different real-life applications, and for example in physics, where we have the derivative of distance being velocity and the derivative of velocity being acceleration. Hence, in order to study the rate of change in distance, we use velocity. With this, and tangent helps study the graph and function much better. With this, a tangent is a straight line that best approximates the curve near that point, and therefore the gradient of a tangent at that particular point of the graph is the gradient of the graph at that particular point, and hence for all non-straight graphs the gradient changes with respect to the time, and the gradient of the various points can be found by finding the gradient of the tangents. With an example can be taken here, where the graph shows the equation g of x as equals to g of x as the tangent of the f of x. F of x is x squared minus 5x, and g of x is x minus 9 at point of x equals to 3. With this, the gradient of the slope of the f of x at x equals to 3 is 1, as shown that the slope of g of x is 1. Continuing on, these are important functions and their derivatives as derived from Harvard University. F of x is the derivative of f of x is x of x prime, and these are the differential rules, and there are additional rules: scaling rule, product rule, quotient rule, chain rule, and the easy rule of simplifying everything through deriving. With these differential equations are equations containing such functions and derivatives of these functions, and the order is different from highest to lowest, and they're classified into different categories, that is ordinary and partial. For ordinary, there are functions that are ordinary derived, and that is fully and ordinary, while for partial, they are partially derived due to its elements. They can be classified under first and higher. They can be linear or nonlinear. However, only linear equations are homogeneous or inhomogeneous. These are examples of differential equations.
The problem we are going to talk about is bacterial growth. First, what is bacterial growth? Bacterial growth is the division of one bacterium into two daughter cells in a process called a binary fission. Why bacterial growth is so important? So now, we needed to talk about bacterial growth because in the microbiology company they need to use characters for calculating the number the number of bacteria and the time they can use for getting exact number of bacteria. So this is the bacteria curve. So first, before we go into the bacteria curve, those produced bacteria are used in different areas, like in medicine, in producing antibiotics, in plant growth, or other natural product at an industrial scale. So bacteria growth curve has four phases. Now we are going to talk about two phases of them, where the characters are applied. Exponential phase and the depth phase are where characters are applied. Exponential phase, as time increases, the number of bacteria produced are increased, and on the depth phase, as the number of bacteria produced, as the number of time increase, number of bacteria produced reduced, as you see in the curve. So this is the graph interpretation. So now we're going to talk about this example to show how differential equation and the other calculus applied in bacterial growth. Suppose a population of bacteria double in size every 11 hours. Initially, there are 200 bacteria cells. If you began growing the bacteria for our experiment at 7 p.m. on September 4, when it's less than necessary 5 million bacteria cells will be ready. So the company need to know how long it should take to produce 5 million bacteria cells, while every 11 hours the initial population doubled. So we given this formula as we see here, differential equation are referred to this formula. The population over the time equal to rate times population. This is rate. And the bacteria double for 11 hours as we get seen the problem, and the initial population is equal to 200 is the formula. Then by separating variables and integrating it, we get this. We will see we're separating and then we integrate both sides, and we get this formula. This is constant. Then as we have initial population equal to 100, by replacing we see for initial population is time it is equal to 0, then we get a constant is equal to 200. Then substituting into the formula, get here this a given bacteria double for 11 hours, and then after 11 hours it means that time is equal to 11 hours, and then we see that we found that the initial population doubled when we have 11 hours, which is equal to 400. Then by substituting it for looking for key, this rate for doubling, we get to 1 over 11 ln of 2, which is approximately 0.063. Then by replacing key by its value, we get this. Then now we are looking for the time when the population is equal to 5 million. We replace everything and then we get time is equal to 160.70 hours. Then which is converted into days, we get 6 days, 17 hours. And then we know the initial time it was 0. Then by adding it, we get this. The production will stop at 12 p.m. of September 11. Yeah, thank you. This is another exercise we can work on for getting experience.